Today's video we're going to talk about valence electrons. Now, normally valence electrons are one of the more difficult concepts that we cover throughout the school year. But we're going to do our best to present it in a way that makes a whole lot of sense to you. So the first thing we want to do is a review. Let's talk about just the things that we know so far. So we know that there's something called an atomic number. The atomic number tells us the number of protons in the atom. Now, why is the atomic number also important? It's more than just that it's the number of protons. It also that the number of protons tells you the name of the atom. Okay. We also have something called the mass number, or the atomic mass. Okay, two things have mass in an atom, and they're both found in the nucleus. We have protons and neutrons. Okay, not electrons. Electrons are so small that their mass is what we consider to be negligible. It's not even worth measuring. Okay, and so we also have these things called electrons, though. Even though their mass is negligible, they do exist. They are found outside of the nucleus. Remember, everything has a mass associated with it and a charge associated with it. So if we were to talk about protons, neutrons, and electrons, we would say that protons have a mass of 1. Neutrons have a mass of 1 atomic mass unit, 1 AMU. But electrons, it's negligible. It's close enough to 0 that it doesn't matter. If we talk about charge, however, that's a different story. So if we talk about charge, protons have a positive charge. They have a charge of +1. Neutrons have a charge of 0. They're neutral. Be very careful with that. A lot of people mess that up. Don't make that mistake. They're almost the same word. Neutrons are neutral. And electrons have a charge of -1. Both neutrons and protons, we said, were found in the nucleus. Okay, these are outside in the electron cloud. Okay, so we're going to start with what was probably a pretty ridiculous story, but you're going to see that eventually it makes sense. So if we start at a football stadium. Okay, we have a football stadium right here. And inside the football stadium, right outside the football stadium rather, we have parking lots. Okay, and inside each parking lot we can hold a certain number of cars. Now the parking lot that's closest to the stadium, where the players and the referees and everybody park, that's really important, the VIP lot, is rather small. So this first parking lot right here, we're going to call parking lot number 1. In this parking lot we can only hold 2 cars. Now, I know that's kind of a ridiculous example, but it's going to work as with our metaphor as we talk about what's going on in the atom. So just kind of play along with me for a little bit. Because this type of parking lot is so small, let's say they named it an S lot. Now, the further out you go, the parking lots are going to get a little bit bigger. So as we come out here, we move out and we have another S lot, but there's also a larger lot associated with it. And this lot we're going to call a P lot. And this one can hold 1, 2, 3, 4, 5, 6 cars. And this is in parking lot 2. So this is parking lot 1, this is parking lot 2. So how many cars can they hold in total? Parking lot 1 can hold 2 cars in total. Parking lot 2 can hold 8 cars in total. Alright, so we go out a little bit further, and the third level of parking lot is very similar to parking lot level 2. Okay? It has the same exact number. It is parking lot level 3. And it can also hold 8 cars. So let's say this is a Houston Texans stadium, NRG Stadium, and there's a parking lot attendant who works in each of the 3 parking lots. Okay. And so the rules that the Texans have made about the parking lots, they say that if a parking lot is completely empty, there's no point in having an attendant there. And so if the parking lot is completely empty, They're going to let the attendant go home, but they're going to give him a small bonus for coming out for his time. So it's really great for him. He gets paid and he doesn't have to do anything. Now, if the parking lot is completely full, every spot is filled, then he did a good job. He was out there giving cookies and waving signs and got everybody to come in there. So he's going to get a bonus for that. Also a really good thing. But if the parking lot is partially full, then he does not get a bonus in any way. So let's say we have a car down here. Okay. And we're going to start filling in the parking lots here. Let's just get this together. So let's say this car comes out and he parks in this parking spot right there. Is the parking lot attendant in parking lot level 1 happy right now? Well, no, he wouldn't be very happy at all, right? He is not getting a bonus. If it was completely empty, he would get a bonus. Or if it was completely full, he would get a bonus. Neither one of those is the case right now. Okay? So, let me just do this real quick. All right, so he goes and he waves a flag around and he gets a second car to come into his parking lot. Now he has 2 cars in his parking lot. So is he happy right now? Yes, his parking lot is completely full. So he's getting everything he wants. He's going to get a bonus. Is the parking lot attendant in number 2 happy? Also happy. There's nobody in his parking lot. He gets to go home and gets a bonus as well. Okay, now what I'm going to tell you is that this has nothing to do with a football stadium. What we're really talking about here is we're talking about atoms. Right? If you look at an atom, you can see we have different energy levels where electrons might go. 2 go in the first level. You notice they have an S designation just like our S parking lot. 8, 1, 2, 3, 4, 5, 6, 7, 8 go in the second level. Notice that 2 of them have an S designation and 6 of them have a P designation for the orbitals that they're in. So you have 2S and 2P. There's 6 of those. Okay, so let's say we're going to use an example of oxygen. Okay, so we are going to bring oxygen. Oxygen, you'll notice right up here, has an atomic number of 8. Okay, so let's go back to our diagram. We're going to make this one oxygen. Has an atomic number of 8. If it has 8 protons, how many electrons would it have to be neutral? So if we have 8 pluses and it's a neutral atom, how many minuses would we have? It would have to be 8. Number of protons and electrons are neutral, or are equal as long as it's in a neutral atom. Okay, so we're going to start dragging these electrons out here. Let's say we have 1, 2. You're always going to want to park in the parking lot that's closest. 3, 4, 5, 6, 7, and 8. Now, if this was a stadium, would he be happy? All right, if we go back to our stadium, would he be happy? He has 1, 2, 3, 4, 5, 6, 7, 8. Is that parking lot attendant happy? No, he's not. He still has 2 spots that need to be filled. Now he has a choice. He could either try to get rid of 6 cars, or he could try to attract 2 more cars. Which do you think is going to be easier? Getting 2 more cars would be easier. Okay, so let's go back here to this atom. So this atom would be more stable if it had 2 more atoms. All right, let's pick another stadium. Okay, in this case, we have a stadium that has 1 car in it. So we're back at our old stadium over here. And he realizes, this parking lot attendant realizes he's not going to make it. So he calls up his brother-in-law, who owns a wrecker service, and he says, "Hey man, I'm in deep trouble. I want to get this bonus. I got things I need to do. I got bills. Can you help me out? Do you know of anywhere I can get a car?" He says, "Yeah, man, we have a cousin who works over at the soccer stadium." So, "Oh, I mean, can you help me out?" So he says, "Yeah, I can." So he goes and he calls his friend over here at the soccer stadium, and he says, "Hey, can I tow that car?" And this parking lot attendant would be thrilled because then he's going to get a bonus. If this car leaves, he's going to get a bonus. So this car gets towed away over to our other stadium. Now he has 7 cars, but he still needs one more. So he calls his brother-in-law again and says, hey, I need one more car. Is there anything you can do? So he goes over to the basketball stadium, and they find one car in one of the parking lots. He says, yeah, I think we can do this. If we can bring one car over, we're going to be good. So he takes this one car, he tows it over. This parking lot attendant's happy because he left this parking lot empty. Brings over one more. Now, is he happy? He sure is. Look at that. All of his parking spaces are full. All of these are empty. He's getting a bonus. Now let's take a look at what that would look like in the atomic world, in the atom model. So he has 8. Right? If there was another atom that only had 1, well, let's think about what atom that would be. If it has 1 electron, if it's a neutral atom, we have a -1. How many pluses would that be? Be 1. So it has an atomic number of 1 mass. So if we were to look at our periodic table again, it has an atomic number of 1, right? We're going to find out that that is hydrogen, right? Right here, hydrogen. All right, so let's go back to we have 1. So this atom, is it stable like this? It has 1 electron in this shell, right? It needs to have 2 or it needs to have 0. So it decides it's easier for me to give this away. Now I have 0. And he gives it to our oxygen atom, and he takes 1. But it needs another. So it finds another hydrogen. And it takes that electron, and it brings it over, and now it has 2. Are all of its shells full? Everything in shell level 2 is full. We call the outside shell that has electrons, we call that the valence shell, and those are valence electrons. Valence electrons are the electrons in the outermost shell. Okay. Now let's take a look at what just happened. We had 2 of these hydrogen atoms had to give their electron to 1 oxygen atom. That sounds like something familiar, doesn't it? We had 2 hydrogen atoms with 1 oxygen atom. That's water. That's why water forms. Okay, let's take a little bit of a jump here even further. Let's bring in another valence shell. So we know that if we have 1, we have 1 electron, this is hydrogen. Atomic number 1. What if we have lithium? Atomic number of 3. Let's drag them out. 1, 2, 3. How many valence electrons? Electrons in its outermost shell. 1. We have 1 valence electron. Just like we had with hydrogen. Okay, what if we go to sodium? Atomic number of 11. Okay, so let's start dragging them out. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How many electrons are in the outermost shell? There's 1. Again, 1 valence electron. Okay. Remember, sodium, lithium, and hydrogen all had 1 valence electron. Let's take a look at our periodic table again. So if we look, we notice that hydrogen, which is in the first group, has 1 valence electron. So does lithium. So does sodium. Do you care to guess how many valence electrons cesium has? One valence electron. Matter of fact, everything in that group has one valence electron. So if I look, everything in here has one valence electron. All right? Even more so, if we keep going, guess how many electrons you have in this group? We have two. Now, we're not going to deal with everything in these transition elements right here. This is what I like to say is high school's problem. We're going to deal with these when we get to high school. It's not any more complicated, but it's not something we're ready to deal with just yet. In this group, we have three valence electrons. In the representative elements, you have one valence electron, 2, 3, 4, 5, 6, 7, 8. Now, if they have 8 valence electrons, that means 1, 2, 3, 4, 5, 6, 7, 8. Their outside shell is full. Are they going to want to get any more electrons? Nope, they are completely stable. These are very stable elements. These are known as the noble gases. These have 7. If they wanted to be completely stable, they would want to get to 8. So if they have 7 valence electrons, who are they going to most likely react with? 7s are going to react with 1s. Right? The alkali metals are going to react with the halogens, 7 plus 1. So we'll get sodium, Na, reacting with Cl, chlorine. NaCl is salt. Boron has 3. Who do you think it's going to react with? It's going to try to get to 8, so anybody that has 5 is who it's going to react with. Boron would react with phosphorus. What's special about the 4s? 4s are trying to get to 8, but 4s will bond with themselves. That's what makes carbon such an important element in terms of our organic beings. Anything that has carbon in it that isn't carbon dioxide is an organic molecule, because carbon is just so good. It's like the Lego of the elements. It will bond with anything. So 5 minutes ago, you may not have had any idea of what a valence electron was. Now you can pick up any periodic table and you can say calcium, which has 2 valence electrons, would bond with selenium, and you could explain why that would happen. One other thing that's really handy, if you're taking a test and you can't remember how many electrons are in each shell, take a look. When we went back to our first energy shell, we had 2. Right? Let's look at another periodic table. Look, how many are in the first energy shell? 2. How about the second energy shell? When we were in the second energy shell, it had 2 in the S, 6 in the P. We have 1, 2 in the S, 1, 2, 3, 4, 5, 6 for a total of 8 in the p orbital. The third energy shell is the same way, 2 in the s, 6 in the p orbital. Like I always say in class, it's difficult to memorize facts. It's much easier to memorize stories. If you can't remember how many electrons are in each orbital, that's okay. The periodic table will tell you these are the s orbitals, these are the p orbitals. And it's going to tell you how many electrons there are. 1, 2, 3, 4, 5, 6, 7, 8.